Dr. Shamaei, for me.
Yep. Thank you. Today I would like to present a work on the estimation of quasi-stiffness of the knee during level ground walking that could be used for development of lower extremity prostheses and orthoses and assistive devices like exoskeletons. Okay, let's start with moment and angle graph of the knee. First, heel contacts the ground at point A, and then it flexes up to point B. Previous studies shows that this phase is a linear phase. Okay, so if we fit a line to this phase, the slope of that line would be called the quasi-stiffness of that phase. Similarly, for the extension phase, we can define the quasi-stiffness, and also for the weight acceptance phase of the gait. Our previous work shows that the quasi-stiffnesses of the knee are both user-specific and gait-specific. Especially if the gait speed, for instance, changes, the quasi-stiffnesses of the knee also change. Also, for different subjects with different weight and height, we have different quasi-stiffnesses. Therefore, ideally, an assistive device should tune its stiffness to based on the gait conditions, gait speed, ground slope, or subject's weight and height to ideally mimic the gait of that subject. But for a specific gait, if we have the moment and angle data of that subject, we can calculate the quasi-stiffness of stiffnesses for that subject. But usually the design centers don't have gait lab data, and also the patient cannot walk in gait lab data, even if they have it. So the idea is to have a set of mathematical equations that can give us the quasi-stiffnesses of the knee for a specific subject and under specific gait conditions. In other words, these equations would get a set of measurable parameters like gait speed, weight, height, and joint excursion, and give us the quasi-stiffnesses of the knee. So we started with an inverse dynamics analysis of the knee. From ground reaction force and moment, we calculated the generic equation of knee ankle moment and reaction force, and with those we found the generic equation for the knee moment. And then we simplified this generic equation for the instant of maximum flexion, and we found that the knee moment in this instant is a function of weight, gait speed, and height. So previously we said that the knee in the flexion phase behaves linearly. So the knee moment would be the slope of that line multiplied by the joint excursion in that phase. And similarly for the extension phase. Therefore, we have two sets of equations with identical left-hand side. So the right-hand side should be equal. From these two sets of equations, we came up with a set of key parameters that can potentially explain the knee quasi-stiffnesses. But yet, we don't have the actual relationship. So we employed a set of extensive experimental data, mainly from 14 subjects, and we applied linear regression, and we came up with the actual general model that can accurately explain the knee quasi-stiffnesses in the gait for different subjects. Here you can see the results of these models for one of the subjects with the reasonable gait speed. One of the interesting findings out of this research was that we found that almost all subjects exhibit identical quasi-stiffnesses in the flexion phase and extension phase at the preferred gait speed. In other words, the knee tries to employ a spring-type behavior at the preferred gait speed to maximize the energy recovery. We went on and we simplified these models for the optimal gait speed, and we found a set of equations that can predict the knee quasi-stiffness for the optimal gait speed for subjects with the weight and height that are given. And you can see that the error of these equations are pretty low. Here in this graph, you can compare the results of our models with the actual quasi-stiffnesses for 14 subjects. So in this research, we came up with a set of equations that can closely predict the knee quasi-stiffness for different gait speed. And we also came up with a set of stature-based models that can give us the quasi-stiffness at the preferred gait speed, and they could be used as a starting point for the design of lower extremity assistive devices. I also found that the spring type behavior for the knee can partially define the optimal gait speed. At the end, I would like to thank our funding resources, and if you have any questions, I'm happy to have it.
Thank you for the presentation. In your approach, you're assuming that the knee joint torque is depending on the knee joint angle. Correct?
I don't assume that. But what we did was that first, based on inverse dynamic analysis, we came up with these parameters. We found that the knee is a function of weight, gait speed, and height. And also, we showed that the knee in this phase, in flexion phase and extension phase, behaves linearly. Therefore, the moment of the knee should be equal, should be approximated by the slope of that line multiplied by the excursion in that phase. So now we have two sets of independent equations, but with identical left-hand side. So we combine them together. And when we combine them together, then the joint excursion appears here.
Could there be also an effect on the other joints, like the hip joint or the ankle joint, influencing the knee torque?
What do you mean exactly?
Like the muscles crossing the knee joint, monoarticular muscles or
Right.
biarticular muscles. Do you have an idea what is the contribution? Like this looks like a monoarticular approach. How much this contributes to this?
It is on an upper level. It doesn't go through the muscles. We just purely focus on the moment and angle behavior of the knee, only in level ground walking. So basically, we don't go through that.
So the result shows the gait-specific stiffness, right?
Gait-specific stiffness.
How is the user-specific stiffness implemented here?
With weight and height, when we have these two parameters, we say that it is user-specific. So if we have the weight and height of, let's say, an amputee, then with these equations, we can choose a spring or for the design.
Right.
No, we don't have any. This is just our observation. Out of this, and we found that the slope of these two lines at the preferred gait speed tries to be identical. So, in other words, the area between these two curves would be minimal. No, this is just an observation.